And now, Off the Deep End with Chris Hanna.
Hello and welcome to the next series for Off the Deep End, Gravitational Waves. As with CRISPR, we will be looking at this in 3 segments. The first, what are gravitational waves and LIGO, as well as how LIGO works. LIGO stands for Laser Interferometer Gravitational Wave Observatory. The second segment will be, how have we used gravitational waves, and how have they affected science in the short term, as in right now. The final segment, what will the discovery of gravitational waves enable humanity to do in the future, and similarly, what will LIGO be able to see or measure in the future? So let us begin. I want to start with the device first. I think it will make it easier to understand the concept of gravitational waves if you first understand the mechanics and simplified beauty of this special laser ruler, so to speak, that the scientists from MIT and Caltech have employed. The video link in the description shows an animation to exactly how the device looks, but I will quickly describe it here as well. There is a 200-watt laser, 800 times more powerful than common handheld lasers, that is fired into a beam splitter. That splitter sends 2 perfectly out-of-sync beams outward at an incredibly precise 90-degree angle. They travel the length of 2 arms, are reflected back to the beam splitter, which recombines the beams. Since they are perfectly out of sync, meaning that the high points on the wave of one beam occur at exactly the low point of the other, which means they cancel each other out and nothing but darkness should be visible at the splitter when they return. This is the beautiful simplicity of the device, that they have essentially removed all variables and simplified the equation so that there is only one variable, the length of the 2 recombining beams. I will explain why this is important shortly.
LIGO is really 2 observatories that work in unison and tandem. The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. It produces light that's so coherent that it's capable of detecting gravitational waves.
Despite the purity and stability of the initial beam, it is still not stable enough for use. LIGO's laser needs to be 100 million times more stable than it is intrinsically. To achieve this unprecedented level of stability, the beam's natural frequency variations and other power fluctuations are mechanically reduced by about a factor of 100 million through a series of feedback mechanisms before the laser is used in the interferometer. This whole process is akin to turning the world's most complex piano. LIGO's interferometers are the largest ever built, with arms 4 kilometers long, or 2.5 miles. They are 360 times longer than the ones used in the Michelson-Morley experiment, which had arms 11 meters, or 33 feet long, obviously a precursor to this experiment.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was going to be a very high-risk experiment. It was from its very inception.
If you think about this in the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
This is particularly important in the search for gravitational waves because the longer the arms of an interferometer, the farther the laser travels, and the more sensitive the instrument becomes. Attempting to measure a change in arm length 1,000 times smaller than the width of a proton means that LIGO has to be more sensitive than any scientific instrument ever built. So the longer the better. But there are obvious limitations on how long one can build an interferometer. Even with arms 4 kilometers long, if LIGO's interferometers were basic Michelsons, they would still not be long enough to detect gravitational waves, yet they are. How is this possible?
We have these very massive mirrors. They weigh 40 kilograms, which is about 88 pounds, and they're just the purest material you can imagine.
This dilemma was solved by adding something called Fabry-Perot cavities to the basic Michelson design. Each arm has a Fabry-Perot cavity. It is created by adding mirrors near the beam splitter that continually reflect parts of each laser beam back and forth within the 4 kilometer long arms, about 280 times before they are merged together again. With these Fabry-Perot cavities, the LIGO's interferometer arms are effectively 1,120 kilometers long, making them 144,000 times bigger than de Michelson's original experiment.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
This bit of mirror magic greatly increases LIGO's sensitivity and makes it capable of detecting changes thousands times smaller than a proton, all while keeping the physical size of the interferometer manageable. I will explain why this is important shortly. Started in 1990, LIGO's first iteration was significantly simpler than that of the current aLIGO, which is Advanced LIGO. The main differences have to do with the mirror technology mentioned a moment ago. At the end of the 4-kilometer arms, the mirrors were originally hung using specialized wires, and the glass was manufactured to the optimum performance of the times. Now, after realizing that noise or vibration from the outside world were interfering, the second iteration was completed with reducing outside variables as one of the main goals. The new pendulums at the end of each arm are electronically stabilized. The wires are a special fused 0.016-inch diameter silica, or 16 thousandths of an inch for my fellow science geeks. And the mirrors are of the highest precision ever made. There, that is enough about this device. Now for the gravitational waves and how they are measured using this incredibly sensitive calibration equipment. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will. Nobody really believed that you could ever detect them because the size of the effect is so small.
Albert Einstein predicted the existence of gravitational waves in 1916 in his General Theory of Relativity. Einstein's mathematics showed that massive accelerating objects such as neutron stars or black holes orbiting each other would disrupt space-time in such a way that waves of distorted space would radiate from the source, like the movement of waves away from a stone thrown into a pond.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Furthermore, these ripples would travel at the speed of light through the universe, carrying with them information about their cataclysmic origins, as well as invaluable clues to the nature of gravity itself. The strongest gravitational waves are produced by catastrophic events such as colliding black holes, the collapse of stellar cores, supernovae, coalescing neutron stars or white dwarf stars, the slightly wobbly rotation of neutron stars that are not perfect spheres, and the remnants of gravitational radiation created by the birth of the universe itself.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you made this long enough, if you didn't make it a little pipsqueak thing like this, but you made it sort of kilometer scale, you could probably get these extremely precise measurements.
That was Rainier Weiss, by the way. He created the concept of measuring gravitational waves using the interferometer method. Anyway, the concepts that he described can be simplified imagining a small square. When gravitational waves passes through that small square, it is stretched to be wider. But when that happens, the height of the square shrinks, making it no longer a perfect square but slightly rectangular. The wave then does the same thing in the inverse, stretching the height longer and shrinking the width smaller. This cycles, starting small, getting larger, and then smaller again to silence. These vibrations can also be analyzed directly into sound. So here is what two black holes spinning around each other at almost the speed of light before combining to make a single stable black hole sounds like.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
Now finally, how LIGO measures gravitational waves. If you imagine the square we talked about earlier as the size of the LIGO facility, now 2.5 miles long, and gravitational wave passes through the Earth. The LIGO square is stretched and squished. While that happens, the arms are different lengths, only a thousandth of a proton longer than shorter. But that oscillation will offset the wave frequencies in the two laser beams on each arm. That tiny offset means the waves don't perfectly cancel each other out at the recombination point. At that point, exiting wavelength is measured by sensors and is recorded. Many measurements are taken over nanoseconds, and that data will reveal the size of the wave.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
So there you have it, 1,120 kilometer long arms measuring the tiny, tiny variations in a wave made by a beautifully simple and absolutely stable laser. Gives you measurements to 1,000th of the width of a proton, and it measures black holes combining to create waves across the entire universe billions of years ago.
It's a wonderful proof that all of this incredible stuff, that strong field gravity, is in his equations. Just imagine that. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
Thanks for listening, and remember, if you are peering into the darkness of the universe, searching for gravitational waves, we have a light here for you.
This has been another Off the Deep End. Now back to cellar door skeptics.